All right, good morning. Welcome to Microsoft Reactor session on data manipulation and machine learning with Python. My name is Brian Sletton. I'm coming to you from Northern California, where it's 4 o'clock in the morning. So if I sound a little funny, that's probably what's going on. But welcome to this session. This one is a continuation of some of the other learning paths that have gone on before, including the one that we talked about last week. One is called the role of Python in the space exploration. So if you are watching this and haven't gone through that, that may be something to go through afterwards to get you comfortable with the tools that are being set up that we will be using later, Visual Studio Code and some of the Python installations. And it'll also include some sessions on just getting you comfortable with the Python language, which is a very common and widely used programming language in the machine learning and data science space. So today we're going to continue on and within the theme of the collaboration with NASA. Last week we talked about reading in some data about rocks and moon rocks, and today we're going to talk about some of the considerations that go into planning a rocket launch and how perhaps with the data that we can collect over time, machine learning may help with that process, right? So clearly there are environmental effects, weather patterns and things like that, location of a launch site, and we may want to be able to determine in the future, what would that look like? You know, is this one day better than another to plan for? Because obviously you don't know until you get closer what the actual weather is going to be like. So we'll talk a little bit about the setup of the process, and then we will go through some code to get the data cleaned up and prepared for machine learning analysis. And then, because we don't have a whole lot of time in this session, we're going to then encourage you to continue on and do the final section, which will be the actual machine learning and classification phase. So that's the plan. We have a link to the session, the learning path session. So if you want to follow along there or have that to bookmark for later, we will share that in the chat. But otherwise, I'm going to move on to the first section. All right. So the idea is it's a very time-consuming, expensive process that takes a long time to get ready for, to launch a rocket, and the conditions are obviously unpredictable far in advance. So the idea is, now that we have a couple of decades worth of launch data that NASA has collected and can analyze, hopefully future launch sessions can be predicted better in terms of the likelihood of the situation being favorable. Now, obviously, nothing at this level or scale is static, and we're seeing the impact of climate change. So that's impacting weather patterns and things, so that the data that we have in the past may be suggestive of what might be possible, but we also would want to have it be updated with new data that we're collecting along the way. And so we also want to continue to learn and see how we're doing over time, potentially. And there may be other additional data sets or data factors that we weren't considering in the past that may make us better at predicting the likelihood of a launch or the likelihood of there being some kind of issue. So NASA has obviously chosen places like Cape Canaveral on the east coast of Florida, because even though there are a lot of uncertainties with respect to hurricanes and storms and temperature and whatnot, most of the time it's pretty nice. Most of the time the weather temperature doesn't change quite a lot. Again, with materials and their expansion and contraction and all those sorts of things, they don't want to have a whole lot of variability in the process. So even though, you know, with hurricane season being quite dangerous, there are a lot of positive reasons why they would choose a place like Florida as well. Positionally, they want to be close to the equator in the launch as well. So in this section, we're going to talk about what kind of things can impact these launches. We'll talk about how, as a data scientist, you might approach a project to analyze this data and how you would think about it. We'll talk a little bit about how machine learning factors into the process as well as some of the ethical considerations of making predictions and making sure people understand what's going on. So as we said, NASA now has several decades of launch history that they can go back to. In those early days, obviously meteorological predictions weren't as good then as they are now, and it would be a little bit more variable. But the idea is, as these things occur over time, as we know what the conditions were when things were launched, and as we can connect those to larger patterns, the idea is that we would be able to do a better job moving forward. Now, they obviously have data that they're not going to share with everyone, but they do share a lot of their data. And they also work with the National Oceanic and Atmospheric Administration, known as NOAA. And NOAA, among other things, keeps track of this information and makes it available. So as you can see on this section of the document, there are links to their APIs. And if you wanted to play around with historical weather data from various parts of the world, that would be an interesting place to go and get some data to learn from. That's really the key part with machine learning, is having good data that's suggestive of your environment or your domain that you're working in. And if it's good, high quality data, that will make it a lot more interesting, a lot more fun, and give you a lot more potential for seeing good results. So take some time to explore the NOAA site there, and data.nasa.gov as an example. There are other governments of the world publish information about weather and labor statistics and things like that. And so you could deal with biological data and economics data and those sorts of things from a lot of these government sites. But so presumably we will go and grab some weather data from this kind of a site, and then try to figure out where there's some signal in the data that could give us a good idea of whether a launch would be more likely or not. So why is there so much variation in the data? It's because there are lots of inputs. We've got satellite sensors, we've got atmospheric balloons, we've got other data sources, we've got sensors in the air, sensors on the ground. And so all of those things have to be collected, they have to be sorted, indexed, connected together. And so that's a value proposition that NASA and NOAA have already done a bit for us. But presumably, you might be finding sources from multiple locations as well. So it's not like everyone's going to hand us what we need and make it very easy for us. I've taught a lot of machine learning classes where some of the feedback was, hey, this would be great if you gave us good, clean data to learn from. And I always think maybe that person's not ready for this, because you have to do a lot of legwork yourself. There's a lot of cleaning and sweeping up to get the data prepared to learn from. So it's fantastic that we can learn from the work that these other organizations have done, but don't for a minute think that you're not going to have to pay attention. As you'll see in a moment, we have to go through and clean the data up ourselves, because there are some elements that are missing. And if we're trying to build patterns from the data and models that absorb those patterns, then we're going to want to make sure that the data is shaped in a way that will not impact the analytics in a bad way. So some of the things that they have collected have to deal with electric fields around the vehicles, the time, maybe it's earlier in the day, weather conditions are one way compared to later in the day. Location, how far the vehicle has to travel based on where on the planet it is and the angle that it's trying to get into in orbit. the temperature of the clouds, the amount of precipitation in the air or the likelihood of precipitation. And so all of those things combine to give them a sense of safe conditions for the launch. And that's backed by other branches of the U.S. government as well, like the Air Force, and they help make sure that all this information is collected and understood and have the sensors to do so. Now, the reason we're talking about that is, we don't necessarily know which of the factors are going to be the most important to us. And so we can't just take data and shove it into algorithms and hope to have some kind of useful outcome. That's almost a dangerous approach, particularly if you're trying to convince people to do something, like to spend money or time, or to make a choice in their business or their lives. So we're going to couch a machine learning activity in a larger data science workflow. And so this is really just about keeping ourselves honest and understanding where the data is coming from and how it was collected and what can we use it for and what do we need and where's their signal and which models are best suited for the kinds of analysis that we want. But key to this is the presence of the business driver and the business understanding. A lot of machine learning advocates and aficionados just like doing that part of it, and they don't always necessarily think about the business outcome. And that's crucial, because one part of the business outcome is to convince somebody of something. If we're trying to decide whether to launch or not, we better have a pretty good understanding of where the data is coming from and what it's telling us and what the likelihood of it being a good result. Because if we cancel something and it turns out the weather's just fine, then we've wasted a lot of money. If we suggest that it's okay to launch and then there's a problem, obviously that would be unfortunate and a terrible outcome. So we're just trying to keep ourselves honest, so that when we have analysis that comes out of the data that we're collecting and we're using it for some kind of larger understanding, we keep that in mind. And so once we have a business understanding of what it is we want to do, then we're going to have the data to collect, the data to analyze. And so there's one part of the process that's about collecting the data and understanding its sources and how it might be used, and if there are any ethical or regulatory or other kinds of issues that we need to deal with respect to using the data, then that's an activity that's part of this process. And it may not be something that you're doing. You may have a data engineering team. You may have some domain experts that are helping feed some of those choices, but somebody has to be doing that. And then there's the more research-oriented modeling part of it, where unless you're very sophisticated in your background, you're probably not going to be innovating on the development of algorithms, but in terms of which algorithm works well on this data set that you have, and in terms of the time, the amount of data, the speed of which it's able to come to conclusions, the quality of the conclusions, those sorts of knob turning activities are what most people consider machine learning. And that is a big part of it. We're just trying to stress the fact that that can't be done in isolation, and the larger context of the questions and that are being asked, and the capacity for you to successfully and accurately and hopefully with some amount of explanation, confidence around what you're seeing with your customer. So we've got the people establishing the business context, we've got the people collecting the data, we've got the modeling activities to try to build some predictive capacity from the data that we have, and then potentially we may either just be telling somebody what we're doing or what we're suggesting, or there may actually be some software to take into production. So think about recommendation engines or some kind of question answering kinds of system. So there's the process of operationalizing those models, and they may involve a lot of data, and they may be slow in terms of the inference step of the calculations. So we have to figure out, does it make sense? Does it fit? Are our customers going to complain that things are too slow? So this is a very complicated process that involves a lot of roles and a lot of expertise. But hopefully that's clear, and that doesn't stop you from exploring and playing around with any of these, right? There's, at the end of the session, we'll give some links to some additional learning paths that will cover more of the data cleansing and setting up kind of activities, and some of the other more specific tasks in each of these steps. And you could find that you enjoy any part of that. And the real goal then is to build a team that has the expertise and the capacity and the experience to tie it all together. But for our purposes, you're going to be our expert, and we're trying to establish some business context around it just to make it a little bit more realistic. So the basic 4 steps that we have here are: start with a business goal, and that will be driven by an understanding of whatever specific domain you're talking about. We're talking about rocket launches today, but that could be new promotions for customers and what would they respond to, or other impacts, in terms of people's appreciation for a product line. What would they like to see? Those sorts of things you may be able to predict based on consumer feedback. But maybe purchasing patterns, or change in demand for certain of your products, that's the kind of thing you're going to want to be able to capture and respond to very quickly if there are changes to those. So once you understand the business context and you understand where there may be an opportunity for a machine learning and data science activity, then you'll go through and start to identify and collect your data, analyze it, make sure that there are no outliers, unless that's something that's factoring into what you're dealing with. Make sure that you understand the acquisition process. If you're collecting information from users, do they consent to it being used in these types of activities? So this is just mostly familiarization with the data. And once you get reasonably comfortable with that, and what's the nature of the problem that we're trying to solve, that will give you a narrower collection of algorithms to use. But that's still going to be on a case-by-case basis, you playing around and saying, well, let's try this kind of classifier, let's try that kind of classifier. But once you get some experience with this, you'll have more of an instinct where to start. But then by using metrics and measuring the outcomes of the training processes, you'll be able to gain some improved gut feelings about that in the future. And then if you're talking about rolling this into production, then once you've demonstrated to the business stakeholders that the outcomes are to their liking, the predictions are accurate enough, then you'll try to roll it out into production. Now, keep in mind, even if you're successful in all of this and you're able to make good predictions, you will have to revisit this deployment of the model, because as your data changes, as your customer patterns change, as the weather patterns change in the launch data, the models will have to be updated. And if the models have to be updated, then the models have to be updated potentially in production as well. And you're going to want to make sure that you have a smooth process in those sorts of transitions. So for our case, we're going to imagine here, just to connect it to a different domain as well. If you're trying to improve your yields, the quality as a farmer of, say, some produce like lettuce, obviously things that might help you make it grow faster, larger, have different kind of taste characteristics would be things like the conditions of the air, the time of the year, the geographic location, what kind of water, how often do you use it, the type of soil, right? These are all the kinds of things that you might factor that go into it. But then when you're deciding, okay, let's try to analyze this data and exploit it, you're going to say, all right, we see these kinds of outcomes in these situations, right? This lettuce grew this big, we had a taste test, and on a scale of 1 to 10, people said, this was a 7. And you may find that there's some kind of evidence that certain characteristics seem to impact the outcomes. And so if in general it takes 1 pound or 2 weeks to run to run one kind of growth cycle, you might want to get it down to 12 days, 11 days, something like that. And if you could do that with better fertilizer or more exposure to the sun, that's the kind of thing that you would want to do, right? So we're trying to establish in this lettuce case what you might want to consider in terms of trying to predict a particular outcome. For our rocket launch case, we want to make sure that we both have good predictions in the final result, right? When the day comes, we can see were we able to successfully launch or not, but we also want to have more confidence going into the predictions what our launch result will be. So we want to have this feedback loop in the process, and that's going to involve us not only looking at the data that we have collected, but maybe when talking to subject matter experts who understand the situation, what else could we collect in the process? So in this case, this is an iterative process, and you may not get it right away, but hopefully the collective expertise of the domain experts, the machine learning experts, the operationalizing experts can work together to produce a consistently good result. Now, obviously, data is a key part of this. There's a lot of metaphors floating about, like, raw data isn't all that useful, just like raw petroleum or raw oil, right, is not all that useful. It has to be refined. There's a similar process here. Like, once you get the data, then you may want to, massage it a little bit to make it more useful. Now, the kinds of manipulation that we do with the data here is not intended to change the output in a negative way. Like, it's entirely possible to transform the data in ways that would predict completely different results. That's not what we're going for. We're just trying to say, if during my first stage I'm selecting the data that I think might be useful, that's called feature selection, but the data may not be in a form that makes it easy for the machine learning algorithms to pick up on any kind of numeric variation. So you may need to change the size of the results. You may need to change the not the size, but the value range. So if one of your data elements goes from 0 to 10 and another goes from 0 to 1,000,000, some algorithms will be sensitive to that variation in scale. So you can rescale things, comparatively, so that you're not changing the way that the data interrelates with itself, but the algorithms may find a better signal in that sense. So we're not trying to change the results in any way other than to amplify whatever kind of underlying information we can extract from the data. And that includes things like filling in missing values and making sure that the units are in the right value space, as I suggested, but also potentially converting features that aren't numeric in nature into some kind of numeric representation. So in the case of our lettuce example, it's possible that periodically our sensors might get interrupted because of electrical failure or some other kind of interruption. And so on a particular day, there may be some missing data. And because a lot of that data will have cyclical aspects to it, in terms of, like, the temperature starts off cooler and then warms up throughout the day and then kind of cools off again. Something like that, which follows a relatively clear pattern, might help us decide if there's missing data. Let's just average the points around it, and that won't negatively impact the analysis. But if we are trying to make some kind of predictive power and we don't have a value, right? So if we add up the values and then we have like zeros instead of more realistic numbers, if the answer isn't zero, averaging around that would be much better than averaging the whole thing with a zero value, because obviously that's going to impact the overall analysis. So when we clean the data, again, the point is to try to use our understanding of the domain to draw some conclusions about that process. In terms of choosing the algorithm, it's really not something that you can expect yourself to be able to do now. You'll just have to, see some examples and watch some videos and see what other people do before you can even hope to have a sense of what to do. But there's this really cool cheat sheet here, and actually we'll share the link to this because it's so useful. This is a workflow to help you kind of ask yourself, what is it you want to do? I want to predict values. I want to extract information from text. I want to make predictions between two categories. I want to make predictions between several categories. And so once you have a sense of where you want to go, then there are some sub discussions about what type of algorithm might you do and why might you choose it. So this is a very, very useful cheat sheet available through the website here. And it might be worth it for you to just sort of capture it and keep it around for your early days in this process. Even later, once you get more comfortable, you'll understand what the different types of classification mean and why you might choose one versus another. All right, in the next unit, we're going to talk about how machine learning models actually go about the process of learning. There's usually some kind of general analysis of the quality of the predictions. How far off are they? How many of your predictions were correct? And there'll be some mathematical way of tuning that knob. So, for example, on a type of analysis like a linear regression, you might collect some data. You might be trying to find a line that fits the data. And the thing that you're trying to learn are the parameters of the line. And as the algorithm goes, it changes things so that the parameters are either better or worse at predicting. And when it zooms in on the configuration that gives it the best results, that's generally when it'll stop. And so I don't want you to be confused that this is like some kind of artificial intelligence brain learning per se. Certainly these algorithms could be useful towards something like that, but that's a much different prospect than what we're talking about. We're just simply saying there's an algorithm that has some configurable parameters, and it's through various feedback mechanisms learning to pick the parameters that produce the best results, right? So it's much more sort of mechanical, not as much awareness, right? This isn't Skynet that's going to get mad at us or anything. So for example, if you're trying to be able to identify a berry in your garden, right? You've got the lettuce that you're growing, you're trying to predict what impact changing parameters in how you feed it, what kind of environmental conditions are around it to improve the speed with which you could grow the lettuce. That's one kind of learning. Another kind of learning might be to be able to classify some produce. So for example, let's say that you come across some berries in a forest and you want to be able to identify additional berries in the future. You would spend some time looking at the berries that you've collected, right? That's your data. And you'll notice that some of them have different colors, different shapes, different sizes. And you could then decide, okay, let's sort these into these kinds of berries. And so like these look like blueberries, these look like raspberries, these look like strawberries. So somebody has gone through the process of classifying these things over time. Like strawberry is a class of fruit that has, these particular characteristics. And so if we have some berries that we've collected and we have some characteristics about the berries, size, color, shape, things like that, and we know whether it's a raspberry or a blackberry or a blueberry or something, then a machine learning process might learn to associate the characteristics of the individuals with the class of berry that it belongs to. And so this is kind of how machine learning works as well, right? We collect some data, and there are characteristics like the temperature on a launch day, the wind characteristics, things like that, and then whether it was successfully able to launch or not. So there is a known outcome. Some people call that ground truth. This is a blueberry. This is a blackberry. This was a successful launch. This was a non-successful launch. And the machine learning algorithms are then sensitive to finding the relationships between those inputs and those outputs, right? And so that's the kind of learning that happens. And so as this website has a little example of how you might go about learning to identify these berries, it's not all that different. No, I mean, it's obviously a different approach, but mathematical versus sort of intuitive, however humans learn things. But the idea is we're trying to draw conclusions based on evidence that we've seen, and that's a process that is a significant part of what machine learning is able to do. Now, occasionally, you may come across a new type of berry, and you might say, "Hey, I've never seen a berry of this type before." And if that's the case, then your models aren't going to be successful at making those predictions. So we have to have evidence of the things we're trying to predict in order to be able to be successful. And so the idea is, if your collection process does not include everything that you need to be able to deal with in the real world, then your analytics are going to be underwhelming as well. So for the berry cases, if you don't train on data about a specific type of berry, then you're not going to be successful at predicting that berry in the future. You can't know what you've never seen evidence of, and that's true for computers and humans. And so you have to review the process periodically to see, is this comprehensive? Are there things that we're missing? And so with respect to our NASA launches, you can imagine there are quite a few more successful launches than unsuccessful launches. And for our purposes, an unsuccessful launch is just one that was delayed because of weather conditions or something. So if we're trying to find evidence of the dates that we don't have launches on, we're going to need to make sure that we have that kind of evidence, because otherwise we can't draw conclusions because we haven't seen it. So the whole point here is this is a process. It's not just here's some data, shove it in the algorithm, look at the results. We have to see, are we measuring the same things? Are these berries measured against the same units of size that we're using these other berries? Do we have sufficient representation of the various berries? Do we have all the berries that we need to consider? So those are the kinds of things that the data engineering, data science, machine learning loop helps us with. Is here's what we have, here's the quality of the results. Okay, let's go back and collect some more data, or shape it, or manipulate it somehow, or change our input process. This isn't just a one-shot thing and then you're done. It's an entire approach to learning from the data. So that's what's being discussed here and on the slides, or in the documentation. So assuming that you do a good job of collecting your data and you have enough evidence there to draw some conclusions from, then you're going to want to check yourself and make sure that you are right to have confidence in the outcome. And one of the ways you can do that is to go through what's called a training and test process. And the reason that's important is because if we have this data that we're training from and we know whether something is successful or not, or what type of berry something is or not, then we're going to measure how well we do predicting the data that we have. And the problem is some models are very good at memorizing details. And the problem there is, just like, as I've said in the past, if a child finds the answer sheet to a test, then he is going to look like he did a very good job studying for the test. It's hard to know, did he actually study for the test and learn the things, or did he just cheat because he found the answers, right? And if we're trying to make business decisions on the outcomes of these things, then we want to have some confidence in terms of how we came to the conclusion. So by using up all of our data for the training process, then we have no sense of how well does the algorithm generalize to data that it hasn't seen, because it's seen all the data. And so that's why we generally break it up into two parts. It's usually something like 70-30, 80-20, but there are some other considerations through that process that you need to deal with. So some of this data we keep off to the side. We go through the whole training process. We get excited because we're doing a good job. And then we take that model and then we feed it with the inputs of the test data. So this test data was never part of the training process. And then we look at the quality of the outcome. If it says this is a blueberry and it's right, and it does that enough times, then we're pretty comfortable that we've learned some patterns from the data, and it generalizes well to the data that it hasn't seen before. Because otherwise, the model just might be like the kid learning the answers, and then because it's given the answers, and then just spitting those back out. We want to make sure that's not the case. So that training and test process can get rather elaborate in terms of how you slice the data up and what data is training and what data is test. But we'll, in your third module, which we're going to have you hopefully do at home, they'll walk you through that process a little bit, how to do that with the data. All right, so part of the outcomes of that step is not just the model, but hopefully some confidence in the model. Because in the end, people are maybe going to be making decisions off of the analysis that you're doing. And you want to make sure that they're comfortable doing so, that they understand money could be on the line, people's lives could be on the line in terms of the successful launches or not. So this is why it's important to be clear about the process. One of the reasons why the form that we're going to talk about, Jupyter Notebooks, is so interesting is because you can mix storytelling and narrative with code, so that you could say, here are the assumptions that we made, and here's why we did this transformation, and here's where the data came from, right? Those sorts of things are important towards everyone collectively being comfortable that the model is doing a good job, that it is suitable, that the data quality and coverage is fit for purpose, ready for the task of deciding whether this very expensive thing with maybe human lives in it, maybe not, is likely to be successful and safe in its launch characteristics. Those sorts of things are one aspect of where the ethics in machine learning come in. The data collection process is another part of that. You have to make sure that people are aware that their information is being used in this way, but also to make sure that the entire process is not reinforcing existing, systemic biases or anything like that, which very often they do. And so we want to make sure that before we take it into production, before we roll it out, that everyone is clear about the context, the motivation, the regulatory or whatever kind of oversight there is about the data, the users are aware of this is going on, and that we're all comfortable that this process is ethically and morally sound, right? That's an important part of understanding these. Kathy O'Neill has written a great book called Weapons of Math Destruction, MATH, which is one of the best titles ever, and talks about some of the times that these things can be kind of out of whack. So if you're interested in the ethics of that, there are a couple of great books that have come out on the subject recently. All right, so that's all the big elaborate setup in terms of the process. How do you approach machine learning? How do you collect the data? How do you ground it in a business context? How do you think about the whole process? I hope you found that interesting and useful. There's a quick knowledge check. If you're following along, I encourage you to do it. And if you are logged in, you can keep track of your achievements and get trophies and things like that. They've turned this into a fun learning process. So in any case, I'm going to go back up to the next section, but I do encourage you to check your knowledge and make sure that you're comfortable with what we've talked about so far. So where we are in the process, we've gone through the first module. We're going to now walk you through the next module. And then the third module, we're going to hopefully have you do on your own. That's where the real fun happens. That's where you'll be doing some machine learning and visualization stuff. But I'm just going to try to make sure that you are set up and ready to go and understand the data cleansing process. So in this module, we're going to look at some of some actual data, weather data. It's not necessarily the data that NASA is going to be using to make decisions, but it's suggestive of it and gives you a sense of how you can play around with it. We're going to then use some tools. We'll use Microsoft's Visual Studio Code, which is a fantastic cross-platform development environment. It has extensions for Python, and the particular type of document we're going to be using is called a Jupyter Notebook. So we're not going to be having source code files like something.py or something.js. These are basically JSON files, but they intermingle documentation and code. And normally you would use this in a browser, but it's cool that Visual Studio Code has the extension so that you can run all this directly in the text editor and set breakpoints and things like that. So that's what we're going to walk you through getting all set up. All right, so again, in terms of collecting the data, this is something normally you might have to do yourself, and you would go through and look at these environmental conditions. But fortunately, we're going to have a data set for you to include. It has, overall weather conditions. Things were cloudy, sunny. What was the wind like? What was the temperature and humidity like? Was it raining? And then we're going to see where there's missing values and how do we solve some of those missing values. All right. So again, this is a step in the workflow that will have been done beforehand. You'll have collected this data, but we are going to use an existing data file here. So if you look in this section, which is called Explore the Rocket Launch Data to Gain an Understanding, it's Unit 3 of 8. There's a section called Collect Data, and in that there's a link to an Excel spreadsheet. So this is a set of values where the Microsoft Reactor team has gone through and connected some data from NOAA and the Weather Underground, and then launch information collected from Wikipedia. So they've gone through and presented this for you. Normally, somebody in your data engineering, data collection process would have had to do that for you. So that's being handled in this case. If you open up it in Excel, you'll see it's got these various launch names, the dates around them, whether there was crew data, crew on the launch or not, did it launch or not, the various temperatures. So all that data is in the spreadsheet. But we want to take advantage of some Python code that obviously can't run in Excel. So instead, we're going to load the Excel data into our Python code and turn it into a pandas data frame. So again, this is, if you haven't gone through the previous learning paths, that will walk you through the process of getting your tool set up and working with pandas. But basically, a pandas data frame is like a spreadsheet, but it's a programmatic interface to it. So if that part of what I'm saying is confusing at all, please go back and look at some of the other learning paths. So as we said, the data collection process is key to the quality of the analysis. And in this particular file, you'll notice that there was only one element where things were pushed due to the weather conditions. And that's just a function of the data that was available, how it was collected. There maybe have other ones that were, but our data doesn't reflect that. And I actually remember, I think I was watching when this one got pushed back. So that's the kind of thing where we're going to have a lot of missing results, and we're going to have to fill those in. And usually you're going to want some guidance from experts on that process. Not just making decisions as a programmer. You may not understand the implications of the decisions, but we'll talk about that in just a moment. All right, so hopefully you already have everything installed, but if you have not, then this video is useful. You'll be walked through setting up your tool chain. If you do not want to watch the video, basically the idea is you'll install Anaconda. Anaconda is a Python distribution that comes with a lot of libraries already installed. So it has the Python libraries, pandas, NumPy, some of the visualization libraries are available. So if you have an existing Python environment, if you're a software developer, or if you're new to this is just a nice environment. Everything's prepared for you. It won't impact your other installations. So it's just a nice, good way to go. And then when you configure your visual code, you'll point it to this installation. So if you want to follow the video, go watch the video. But otherwise, it's going to install Anaconda. On Windows, there is an Anaconda prompt, and that will open up with the Conda tool in the path already. If you're on Linux or Mac OS, you may need to set that up yourself. But this is just a tool for managing your distribution. Now, Python allows you to set up what are called virtual environments. So you can install tools and set up some configuration and then switch between them without having to uninstall and reinstall everything all the time. So that's a very easy way to go. So if you run this first command, either on the terminal, if you're on Linux or Mac OS, or in the Anaconda prompt, if you're on Windows, this will create a virtual environment for you. Whatever you name it here, that's what its environment will be. You can specify that you want to use Python 3.7, and then tell it to make sure that that environment has these things installed. So Anaconda comes with these, but in this virtual environment, you can control which versions of things or what's installed. So if you copy this example and run it in a shell or in your Anaconda prompt, that will create the environment. And then to activate it, in essence, to go into that environment, you could say conda activate whatever you called it. So in this case, if you called it myenv up here, then you would use that name down here. Once you're in that environment, for some of the later activities, we're not going to deal with anything right now. You'll also want to install the Azure ML Sdk. So there are a bunch of machine learning libraries that are useful and other just useful tools in the space. that will help you interact with the Azure backend services and things like that. Now, this is something that you may run into, and I ran into. There's another package called XLRD for reading in Excel spreadsheets, and I think it may not support this particular format. So you feel free to do this because it's a useful tool, but I'm going to give you some code that will make things work in just a moment. So once you do all that, you can open up your Visual Code environment and then specify your which Python installation. So for example, up here in the upper right, I have selected this from the collection of various installations that I have on my machine. And so you'll want to make sure that you see the version that you installed, the virtual environment that you gave it. So maybe if you typed in my env, it would say my env and Conda. If you do that, then you're set up and ready to go within Visual Code. There are a couple of other steps, again, on the video to install the extensions for Python and some of the other libraries. I encourage you to watch the video. It's a good, short, useful use of your time. So we've got those extensions installed. Hopefully you grabbed the Excel spreadsheet from the previous page. And so if you open up the directory that you have that spreadsheet in, then you can create a new file, tell it that it's a Jupyter notebook, give it a name, and then if it was just a text file and then you tell it to save it off as a Jupyter notebook, you may need to close the tab and reopen it. But once you do that, you should see all these Jupyter Notebook tools. So again, I'm not going to be able to explain Jupyter Notebooks. We did that in the previous videos, so go back and go through those learning paths, and that will help you understand a little bit better what's going on. But the short version is we have a series of cells. These cells have code in them. We can run the individual code examples, and this is going to be how we're going to walk through the code quickly. All right. So the first thing that we're going to do in this code sample is to load in the various libraries. This is going to make them available to the Python runtime. We're going to alias them for convenience, making the code easier to read. So for example, the pandas functionality will be available through an alias called PD. The NumPy functionality will be available through an alias called NP. In the next modules, you're going to be doing some machine learning using scikit-learn. So we're going to pull in their linear model packages. You're going to be doing some classification. So you're going to pull in a decision tree classifier. And then there's some other tools for formatting results. If you have trouble with the py.plus step here, I had to specify a different Conda Forge source for this. I don't know if that was something specific to my machine or not, but if you do, just Google around installing this and you should be able to find a quick answer to that. Or I should say, use whatever search engine you prefer. All right, so once we pull in the Python definitions and everything, then they should be available to us in the runtime. So I just ran this cell. It flipped by very quickly, but normally you'll see an asterisk in here while it's running. And then if you see a number in there, that tells you that it's done. So this has executed all this code, and we're only going to use a portion of it today, but you'll need the rest for the remaining module. Now this is the part that I had some trouble with the Excel spreadsheet. It said that the XLRDX, whatever that tool was, didn't support XLSX files anymore. So if you look at this code sample that we'll paste into the chat, with the Conda tool, you may need to install this OpenPyXL library for reading in Excel spreadsheets of different types. And then this particular code will read it in and set it up for you. So if you're following along on the website, it just says read Excel and loads it this way. That doesn't work anymore, apparently, in the newer versions. So the version that's being pasted into the chat will set it up. So we're going to read it in as a pandas data frame, and then run the head function to print out the result. So if you look here, we've read in the data. We have a bunch of columns: name, date, the time on the East Coast, the location, was the launch crewed or uncrewed, was it successful at launching, etc. So we've just read the data in from that Excel spreadsheet, and it's in a pandas form. If you have any trouble getting to this format, or into this point, I would say search for discussions about Py.plus. You just have to install it from a slightly different location potentially, but you may not see that. So don't worry about it if you don't see any issues with it. So at this point, the data frame has our data in it. There's a whole series of bits of functionality that you can do to explore the data. If you want to know the columns that are in the data, you can print out the reference to the columns in the data frame, and we'll see all the various names. The names don't tell us the index. I'm sorry, not the index. The units that are associated with them, but with a little bit of exploration, you should be able to figure it out. The info function is interesting because that tells us something about the nature of the amount of data. So for example, we see the column name, but we also see how many non-null values do we have. And we have dates for everything. So we have 300 values there, but we only have names for 60 of them. We only have location, or whether it was crewed or uncrewed, for 60 of them. So here you see the fact that the data came from two different sources, and we merged them, but we merged them and don't have good values for everything. So that would obviously impact the quality of our results. So the next thing that we're going to do is to fill in some of those values. So the basic idea is here, we're going to update the data frame. We say wherever you have any missing values, in the launched column, put a no, right? So basically we know when there was a launch because that data came from Wikipedia. On the days where there wasn't a launch, then it's safe just to say no, there was no launch. So we will now have a Y or an N for every row in that column. For the crewed or uncrewed, again, we know about the crewed ones. So if there was not a crew associated with a particular mission, we'll set it to uncrewed. For unknown, we can set that for the wind direction because we don't know, and there's no way of going back probably historically and figuring that out. So picking a value that is at least consistent is a good result. And for where we don't have conditions on the weather, because Florida is nice most of the time, it would be a reasonable assumption to say fair. If the weather were consistently cold and rainy or something like that, then we would pick a different default value. But the point is that should be what it's like most of the time. So even if it's not 100% accurate, it's hopefully not going to impact the results too much. But that's, again, the kind of thing you would want some guidance from a domain expert to help you make those decisions. So at this point, we've filled in the column-specific missing values. This one just simply says anywhere else that you still have a missing value, put in a 0. Now that wouldn't make sense for strings or categories or things like that, but for numerical data, maybe it makes sense, maybe it doesn't. you'd have to reconsider the analytical impact. So once you go through all that trouble, we should be able to go through and see that we have values for everything. If we run the info example again, notice we now have non-null values for all 300 rows in all the columns. So normally you would want to spend some more thought on that than just filling in a single value everywhere, but mechanically, this is the process that you might go to doing that. All right, and so the last thing that we're going to do is we're going to take our categories and we're going to convert them into numbers. And the numbers are basically going to indicate of the different categories that we see. We'll call this one 0, we'll call this one 1, we'll call this one 2. There's a whole series of strategies for converting categories into numbers, but we're going to be using a useful function called the label encoder from this preprocessing package, and that we imported above. And so we're going to say take the crewed or uncrewed data and encode it to the numeric value associated with it. So that's going to go through and it's going to count how many different values are there, and then it'll start counting at 0 and assign it accordingly. So for each of those 3 results, crewed or uncrewed, what's the wind direction, and what are the conditions, those are all what we call categorical results. They're going to be turned into numbers. So if I look at quickly here, crewed or uncrewed, notice it now says 1 or 0 because we have gone through and encoded that. So where are we in the process? Well, we are wrapping up for today, but we've gone through these first 2 modules. Oh, I'm sorry. So we've gone through and cleaned this stuff up, yes. The next thing that you might do is to see the data that you have, are there other things that you could consider? Is there additional missing data from this other data that you're considering? How would you fill it in? If you want to look at the launch data, you could find maybe some additional triggers in there about the size of the crew or the type of rocket vehicle or things like that that might have had an impact on the launch decision as well. So the point is, we've read the data that we have in, we've made it look better by filling in missing results, but that doesn't mean you're done thinking, right? You should be evaluating everything the whole time in terms of the quality of the results that you eventually get. So we've gone through the first 2 sessions. There's another knowledge check that I encourage you to do to track your progress. But what I hope you do is to then proceed on to the 3rd module, which will walk you through the machine learning process. And so that will get you comfortable using the tools, splitting the data up into training and test data, being able to measure the quality of your results, being able to visualize the results. There's some cool stuff with the PyDot+, and visualizing the decision trees. So please do continue on, right? We've only gone through the 2/3 of the process, but hopefully that will help get you set up. This video will be available, so if you missed something, feel free to return to the video and walk through something. But the documentation on the website is quite good and clear, modulo the changes that I mentioned, and then I'm going to try to get that feedback to the Reactor team so that they can double check whether that's a widespread issue. But you should have given the code sample snippet in the chat room, and also again on the video. You can go back and watch it. So that's where we are. I hope you have enjoyed this. Are there any questions? All right. Well, if you look into the chat, you'll see that there are some next steps. So there's a foundations of data science. There's a getting started with machine learning in Azure Data Science. there's virtual machine learning paths, explaining machine learning models, videos for developers to get them comfortable thinking about these things. Those are all great next steps. And then we are also, there's a survey that we would please like you to fill out to let us know what you liked and didn't like. And the event code is 11898. So thank you very much for joining us. And I hope you have found this interesting. And please come back and join us for other ones. There'll be schedule updates. Check the schedule for new and exciting content to follow along. But there's also things that you can go to the video on the website and just explore on your own. The Microsoft Reactors GitHub repo has a bunch of cool tools and things for you to explore there as well. So thank you very much. Oh, let's see, there's a question here. Cool. All right, thank you, Amin. I appreciate it. All right, well, please stay safe. There's reason for encouragement these days, and let's just all keep safe. So take care, and we'll see you soon.